Welcome all. So, last time we looked into the static buckling analysis, we looked into the dynamic buckling analysis. In static buckling, using the Euler-Bernoulli formulation, we evaluated the buckling load. We looked into the propagation of the buckling, the different loading conditions, the mode shapes that will occur during the static buckling case. After the static buckling case, we looked into the dynamic buckling. We took into account the effect of the inertia terms. We formulated the differential equations. We looked into the propagation of the buckling modes, the dynamic amplification factors, and what is the relationship when the load becomes exceedingly high. So, today we will start with the pulse buckling. So, now we are dealing with the pulse buckling. So, pulse buckling under eccentric loading. So, let us assume that the initial shape due to eccentricity in the system can be approximated by this function, where E is the eccentricity, zeta is the position along the bar, and L is the total length of the bar. So, again we are using a Fourier series expansion. We are using a Fourier series estimate to estimate the initial shape of the system. So, earlier also we have used a Fourier series expansion to estimate the initial shape of the system. And the coefficients a n is given by this particular terms. So, the buckling shape with the time solutions are given by this term. Lambda n is given by alpha and n pi square, where alpha we have already seen, it is a normalized parameter that deals with the applied loading in the system, and tau is a dimensionless time parameter. So, the preferred buckling wavelength is approximated by k star, and k star is approximately equal to root over alpha, and then k star is again related back to the wavelength. So, k star is inversely proportional to the wavelength, and it is given out by this term. So, all sums can be truncated to the dominant preferred mode for the large time. So, as the time becomes large, the dominating mode comes into picture, and all the modes will be near this dominant or the preferred mode. The amplification terms quantifies exponential growth. So, the amplification term is marking the exponential growth in the system, in the buckling amplitude. So, the amplification term G, as we have seen earlier, it is a function of Qn and An, where N is given by the initial imperfections and Qn is the contribution of the buckling modes. So, here we can replace these variables with the bar parameters that are required, and we can calculate the buckling amplitude and the other preferred modes. So, now we are looking into the analysis, the buckling analysis using a conventional finite element software. So, here we are using a LS software named LS-DYNA. So, this is a conventional FEM software used for the dynamic analysis. So, the buckling problem we are formulating in terms of the eigenvalue equations. Eigenvalue equations we know. So, now we are formulating this buckling problem in terms of the eigenvalue solution. So, Km is the stiffness matrix, it is the material stiffness matrix. Kg is the geometrics or the stress function for the initial condition. Lambda is the required eigenvalues or the buckling load factors, and phi is the eigenvectors or the mode shapes occurring in the buckling. The critical buckling load is calculated as the eigenvalue times the applied load. So, the critical buckling load is calculated as the eigenvalue lambda times the applied load. So how does LS-DYNA works? Okay, LS-DYNA is a conventional finite element software. So what it does, okay, in any conventional software, okay, what we need to do is that we need to preload the system. Okay, so for preloading the system, we need to use some sort of static calculations, okay, that are normally implicit to preload the structure so that the realistic stresses are present. Okay, so this is mimicking the initial conditions or the initial imperfections. Okay, after that, the buckling module, okay, is activated, okay, to start the eigenvalue buckling procedure. Okay. After that, we solve the generalized eigenvalue problem, which is an inbuilt code in the LS-DYNA. Okay. And after doing this thing, we extract the results in form of the buckling load factors, eigenvalues, okay, and the buckling mode shapes. Okay. And in order to view the stresses in the buckling shape, we use the certain cards. Okay. So now what we will try to do is that we will try to deep dive into this thing and see how the finite element software normally works. Okay. So in any given finite element software, okay, each will have its own input structure. Okay. So now we will talk about the basic input structure. So for any given finite element software, first of all, a coordinate system needs to be created, okay, or it will be automatically present. Okay. So let us say we have created a 3-dimensional coordinate system x, y, z. Okay. So and the 4th dimension is the time. So once we create the coordinate system, there will be inbuilt elements in the finite element software. Okay. So let us say that there are bar elements. Okay. Inbuilt bar elements will be there, inbuilt solid elements will be there, okay, inbuilt plates elements will be there. Okay. So different types of elemental formulation will be there. Okay. And each elemental formulation, okay, bar, beam, solid, plates, okay, they will have their own localized coordinates. Okay. So each will have its own localized coordinate system. Okay. So now what we need to do is that we need to construct our structure, okay, our given structure. Let us say that we are dealing with a column. Okay. So we need to construct our column made up of this small pieces. Okay. So let us say my column is made up of this small solids. Okay. So what I need to do is that I need to discretize this finite element, okay, and put up n number of solid elements. Okay. So each piece is this solid element, okay, and then connect all this solid element. Okay. So during discretization, okay, normally all things are interconnected in most of the finite element software. Okay. So they will act as a total single unit. Okay. And inside what is going to happen is that each section will have its own matrix formulation, each will have its own stiffness formulation. Okay. And then the stiffness formulation, okay, depending upon the localized coordinate system, okay, so each will have a local stiffness. Okay. So it will have a k local, okay, a local stiffness value. Okay. Let us say it is a small bar. Okay. So k local will be AE over L minus AE over L minus AE over L and AE over L, depending upon the 2 degrees of freedom out here. Okay. So if you are making a system using all these bars, okay, then my k global will be formed, okay, which will be the result of joining of all these 3 pieces of bars, bar 1, bar 2 and bar 3. Okay. And here they will be joined by the choice of my coordinate system. Okay. So the orientation will be, so in the localized system they are like this thing, in the global system they are like this thing. So the orientation will come into picture and the joining with the respective global coordinate system will come into picture. Okay. So they will be joined like this. Okay. So my global stiffness matrix will be formed. Similarly, my mass matrix will be formed. Okay. So this way my first step, that is the geometry, okay, will be taken care of. Okay. So we will create first the geometry of the system, okay, in a global coordinate system. Okay. So, after the geometry is being created, okay, we will give the material properties to the system. Okay. So, the material properties will be assigned to the system. So, let us say we are going to assume that this thing is an elastic material. Okay. So, for the elastic materials we need to give the density, we need to give the modulus of elasticity, and we need to give the Poisson's ratio. Okay. So, these three basic parameters will give to the system. Okay. After we have made the geometry, okay, we have made the geometry of the system, okay, we have given the material properties to the system. After that we need to give the boundary condition to the system. Okay. Let us say we are making this bar and it has a constraint boundary at this end. Okay. So, what we will do is that we will choose all the nodes that formulate as the base of the bar, okay, and we will constrain it. Okay. We will constrain them, okay, and we will say that they are able or not able to move in the displacement sense, or they are able and not able to move in the rotational sense. Okay. So, giving a value of 0 or 1 will allow us to choose the movement of this nodes. Okay. So, we will give the boundary condition to the system. Okay. So, we have given the geometry to the system, we have given the boundary to the system. Okay. So, after that if there is any initial condition present in the system, okay, so normally the conditions, okay, such as imperfections and all are given by some sort of preconditions. Okay. So, we will put the preconditions out here. Okay. We will give them as loading, eccentric loading, or any preconditions that we think will exist in the system. So, these are the preconditions, okay, and we will analyze the system in a static way, okay, and we will take out the results of the static analysis, okay, and use this thing as the initial condition for my buckling analysis. Okay. So, loading definitions we have given as a precondition. Okay. So, after we have the loading conditions from the preconditions, we will put our buckling load, okay, and we will start the analysis. Okay. We will ask it to do the buckling analysis, okay, and this way we will do the buckling analysis for the entire system using any finite element package. Okay. So, in this particular case we are using LS-DYNA, okay, and these are the material cards, okay, that are sequentially put, okay, in the way we have just discussed, so that the conditions, the buckling is analysis is being done. Okay. So, at the end of the day all these cards should be present. Okay. First of all we start with making the geometry of the system. Once we make the geometry of the system, first we make the geometry of the system, once we make the geometry of the system we give the material cards, after that we give any preconditions, okay. After the preconditions we give the loading on the system, after that we ask it to do the buckling analysis, okay, okay, and yeah, in the geometry we also give the boundary condition. Okay. So, the geometry we make the geometry, then we give the material properties, then we give the boundary conditions. Okay. After that if there are any preconditions, we analyze these preconditions normally in a static sense, we use these results to do the buckling analysis, okay. Then we put the buckling load, okay, and after that we do the buckling analysis. Okay. So, these are some of the cards, okay, that are used in LS-DYNA to do the buckling analysis. Okay. So, these are some of the conventional cards. Okay. Any other software will have a similar card to do the same sort of simulation. Okay. Keyword is nothing but it details us this type of cards are there. Static key, it means that we are putting some sort of preconditions. Okay. Control determination means that till what mode, okay, till how many modes we want to run this simulation. Control buckling, implicit buckling tells us that we want to do a buckling analysis. Include geometry simply means that we are importing the geometry of the system that we have made. Okay. Load node set, okay, it means that we are putting some loading on the system so that the buckling analysis can be performed. boundary spec set, it means that we are putting boundary in the system, okay, we are giving it constraints, okay, and depending upon the software the material property is also given, okay. So it can be directly feed into the geometry card also or somewhere in between also, okay. And this is the title of the simulation, we can put it as any title, and after that we perform the entire simulation in LS-DYNA, okay. So the buckling analysis occurs at the simulation termination time, okay. So this is the control termination, this will tell us till how much time we want to run it, okay. So it will run until this specified time, okay. So for buckling at multiple times, we can specify a curve, okay, in this card, in this control implicit buckle card, and the curve's x value marks analysis time and y value marks the number of buckling modes to compute, okay. So for each given time, okay, if you want to run it for several times, we can give it different values of time, and we can give, so in this particular time how many modes we want to calculate, okay. Otherwise we might let it run, okay. So in that particular run time it will calculate the required modes, okay. So this is the procedure to do analysis using LS-DYNA for the buckling mode, okay. So here we are showing a buckling analysis using LS-DYNA, okay. So we are analyzing the buckling of a panel with a bead type of system, okay. So preloading condition, so the panel is loaded to 32 kilonewton using non-linear implicit analysis, okay. So there is already a preload of 32 kilonewton, and that effect of this 32 kilonewton preload has been called is being calculated using a non-linear implicit analysis, okay. So when we perform the buckling analysis, the lowest eigenvalue we got as 12, okay, and the buckling load calculations, okay. So what we have learned is that we will multiply the eigenvalue, okay, with whatever load is given, and we can get the value of the buckling load, okay. The mode shape corresponds to its visualized in the 3D eigenvalue, okay. So this is the mode shape, okay. So if you want to look at physically, okay, what is there is that the system is restrained at a particular end out here, okay. So here we have a panel, okay, basically this is being modeled as a plate, okay. So first a geometry of the plate is been taken, and then this plate is been discretized, okay. So this is how we will start the problem, okay. In starting of the problem, okay, we will take any software, okay, LS-DYNA also or any other software, will make this 4 lines, okay. We will join this 4 lines, okay, and we will say that this has become a plate, okay, or this is a closed surface, okay, with this 4 boundaries, okay. Once we have done this thing, we will click on this plate, okay, or this closed boundary, and we will discretize it, okay, in the horizontal and vertical directions both, okay. So once we have discretized it, we will get this, okay. So it will look like a discretized plate, okay. So now we can click on each part, and each part will be behaving as a plate, okay, but they are interconnected, okay. So once we have done that thing, we will tell this what type of sections we want it to follow, okay. So there are different plate formulations, okay. So depending upon our usage, we can give it as a plate formulation, okay, the appropriate plate formulation, okay. After that, the longitudinal and the vertical directions are given, okay. So the only thing is remaining is the thickness of the plate, okay. So in this plate formulation only there will be a space where we need to specify the thickness of the plate, okay. So depending upon the 2D problem or 3D problem, we can define the thickness of the problem, okay. If it is a 2D problem, thickness is not required, but if it is a 3D problem, we need to define the thickness of the 3D problem, or as is given in the software, okay. Sometimes in 2D problem also we have the option of specifying the thickness of the system, okay. So we specify the thickness of the system. So we have all the 3 dimensions. we have length, breadth and the height. Okay. So, all 3 dimensions are there, and then we have a plate formulation, okay, solid formulation or any other type of plate formulation that we want to use, okay, and we have a discretized plate. Okay. So, once we have the discretized plate, what we can do is that we can choose all the nodes out here and give the constraints. Okay. So, here if you look, okay, this is the fully constrained boundary conditions. Okay. So, it means that all the 3 things are not able to translate also, and they are not able to rotate also. Okay. So, these are fully constrained boundary condition, and in the other zone out here there is a transversely constrained boundary condition. Okay. It means that it can go in this direction, but it cannot move in the other direction. Okay. So, this is a transversely constrained boundary condition. Okay. This direction and the horizontal this way and the vertical this way is restrained, okay, but it can move inside. Okay. So, this is a transversely constrained boundary condition out here. So, fully constrained and transversely constrained. Okay. After that, we need to give the material properties. Okay. So, we can choose any type of material. Let us say we have chosen steel. Okay. So, we need to give the density, we need to give the modulus of elasticity and the Poisson's ratio. Okay. So, we have made the geometry, we have given the boundary constraints, we have given the elemental formulations, we have been given the material properties also. Okay. So, after doing all those things, okay, there is a preload of 32 kilonewton in the system. Okay. So, this preloading is due to this plate. Okay. So, what we do is that we model this plate, okay, we model this plate and we put a preload out here. Okay. So, in this particular system, okay, we do a preloading. Okay. So, we preload the system, okay, analyze this system using nonlinear implicit analysis. Okay. So, we preload the system, there is a preload, we analyze using nonlinear implicit analysis, okay, and the results whatever we are getting, okay, we will use this results as an initial condition for my buckling analysis. Okay. So, once these results are here, we will now do a buckling analysis on this system. Okay. So, once we have performed the buckling analysis, okay, we have just given it to calculate the lowest eigenvalue. Okay. So, this is the lowest eigenvalue that we can see. Okay. Similarly, if we increase the scope of the system, we can look into the other eigenvalues also. Okay. So, this is how we can perform a buckling analysis using LS-DYNA. Okay. So, the similar thing we can do using other software also. Okay. So, for the buckling analysis, what we need to do using any other software is to follow this recipe. Okay. So, in this recipe, first we need to make the geometry of the structure. Okay. Whatever structure we want to make. Okay. So, first we will create the geometry of the structure. Okay. First we create the geometry of the structure. Once we have the geometry, we discretize this structure. Okay. We discretize this structure. Okay. So, if it is a 3D structure, we need to discretize it in all the 3D planes. We discretize this structure. Once we have discretized this structure, so for each element, okay, we need to give what type of sectional properties it is having. Okay. Section solid, section plane, section bar, or whatever sectional properties it is having. Okay. So, once we have given the sectional properties, after that we need to give the material properties. Okay. Once we have given the material properties, then we need to give the boundary conditions. Okay. Then we need to apply the boundary conditions. Okay. After we have applied the boundary conditions, we need to give the preconditions. Okay. If there are any preconditions in the structure, we need to give the preconditions and analyze the system. Okay. We can do a static analysis, we can do an implicit analysis. Okay. So, the result of this analysis using the preconditions will be used as the initial condition for the buckling load analysis. Okay. So, after the preconditions, after we got the results of the preconditions, we will do a buckling analysis. Okay. And from the buckling analysis, okay, after we have performed the buckling analysis, okay, we can visualize our solutions. Okay. And these solutions again we can check with our calculations, with our hand calculations that we have already performed. okay, and the number of, we can control how many modes we want to calculate or how many modes we want to visualize. Okay. So, we can increase and calculate the required number of modes. Okay. Again, this is one more example where we are showing the buckling of a thin walled cylinder under compression. Okay. So, initially what we have done is we have taken a cylinder, okay. It is made up of thin walls. Okay. So, what we need to do is that first we need to create the geometry. Okay. So, the easiest way to do it is we create two concentric circles. Okay. We create two concentric circles and tell that the area between these two circles constitutes a plane. Okay. So, in any given software, okay, there will be an option to call this entire region, okay, in between these two concentric circles as plane. After that, what we can do is that we can extrude this thing. Okay. So, once we extrude this thing, we will get a cylinder. Okay. We will get a thin walled cylinder. Okay. After making the geometry, we need to discretize the cylinder. Okay. So, we will discretize the cylinder, okay, in the radial direction also and in the transverse direction also. Okay. After discretizing, for each element we need to specify what type of element it is. Okay. So, we can give it as a plate type of element, okay, depending upon the definitions of the different plate type of element. Okay. So, we can define the different plate type of elements out there. So, after the plate type of elements have been defined, okay, we can define it as a plate type of element also, and we can define it as a solid type of element also, okay, depending upon what type of problems we are trying to solve. Okay. After that, we give the material properties. Okay. Let us say we are giving it as an elastic property. So, we need to give the density, modulus of elasticity and Poisson's ratio. Okay. After that, we will give the boundary conditions. Okay. Let us say in this particular case, we are giving it as a constraint boundary conditions. So, in order to give the constraint boundary conditions, okay, what we will do is that we will select all these nodes, okay, and for all these nodes, we will say that the translation and the rotational components are 0. Okay. So, we will give the constraint boundary conditions. Okay. After that, if there are any preconditions existing in the structure, we will put the precondition, okay, we will put the precondition and analyze the system, okay, and we will get the output of the analysis using the precondition, and that output we will be using as the initial condition for the buckling analysis. Okay. So, for the buckling analysis, we can specify how many modes are required, okay, or we can let it run for a given period of time and it will show us all the specified modes. Okay. So, here for a buckling of a thin walled cylinder under compression, okay, it is showing the different eigenvalues, okay, and this is the frequency of the system. Okay. So, in this way we can do a finite element analysis and visualize the buckling problem. The buckling frequency will be given by the analysis software again, and we can cross verify it with the analytical solutions that we have got. Okay. So, try to practice these things in the software and good luck. Thank you.